The washer method is very similar to the disk method. The only difference is that the washer has a big hole in the middle. But then the slices which we are using to slice a three-dimensional object of revolution have the form of these washers. And then as we are mathematicians, we are not happy with one washer, and we are also not happy with three washers. We use lots of small washers to build together a three-dimensional object. Let's look at an example here. Find the volume of the solid of revolution, which is bounded by the two functions y is equal to x and y is equal to 2 root x, between x is 0 and x is 4. So here the first challenge is to really understand the problem. So what does a solid of revolution look like in this case? The first function would be y equal x, so this would be just a straight line. The other function is y equals 2 root x, and the root x function looks like this. All right. And now we need to find the intersection point. Let's just compute this. This is where x equals to 2 root x, so we can square, so we get x squared equals 4x. So this means x is equal to 4. So then this point here is directly 4, and this was also given in the problem. So we integrate there. And now we want to rotate this around, make this an object of revolution. So what do we get? Let's plot this again. So then we have the inner thing, and then we have the outer thing, and then this is rotated. So I draw the mirror image down here, and I make this into a coney thing in 3D. Okay, so now we are interested in this object here, this and that, and rotate it around. It is a cone, or it's like a beaker, which has a straight cone inside and a curved cone on the outside. I hope you can imagine what I was plotting here. Let's construct a slicing of this guy. So I plot the functions again. And now I take a little dx. dx is here. So then I get a little element right here. And if I rotate this around, then I get the washer. Okay, so let's take the upper radius maybe here, the lower radius maybe here. So then if I rotate this around, I get something like this, which has a hole in the middle, but it has a certain thickness here and here. Ah, what a beautiful washer. Now I'm interested in this volume here. So again, the small volume, the volume would be the area of this washer thing times dx. Okay, so dx is the width here. How do I compute the area of a washer? Well, easy, right? I take the outer disk and then subtract the whole. So this is area of outer disk minus area of the whole. And so the area formulas for a disk is pi r square. So then we have, this is pi times radius outer square minus pi radius inner square. So far, so easy. Now we need to identify what is outer and what is inner. So the outer curve is given by the root curve, 2 root x. So then this is pi, and let's make a bracket there, 2 root of x, and then all this squared, minus the inner, and the inner is, in this case, y is equal to x, so this is just x squared. Then we can square this out, so we get pi times 4x minus x squared for the area. Then the volume element for the washer, dv, would be area times dx, so this is then pi 4x minus x squared dx. Yeah, very nice. Now we can go on and integrate this. So then we have the volume would be the integral of dv, and so that's the integral over our formula from before, pi 4x minus x squared dx. And now what are the integration boundaries? Let's go back to the problem. Here we said we integrate from 0 to 4. So we integrate from 0 to 4. All right, let's do that. So then we have pi, and then this integrated gives a 2x squared minus x cubed thirds between 0 and 4. So then we keep the pi, and then we sub in 4. 4 times 4 is 16, times 2 is 32, and 4 times 4 times 4 is 64 divided by 3. And if we sub in 0, we get nothing. So then we make this into thirds. Then we have 96 minus 64 thirds. So this would be 32. Pi 32 thirds. And that's our result. So this would be the total volume of this beaker. But of course, it's the material the beaker is made of. It is not the contents which you can fill into the beaker. It is the material the beaker would have been made of. There's one level of symmetry in all this which I would like to tell you about. So you can rotate it around the y or the x-axis. Both is possible. So let me show this just quickly here. All right, so this is the case we did. We had a washer standing on its rim. We can also have objects of revolution which rotate around the y-axis. Okay, and then we would have washers which are laying down. It's the very same principle, but you need to be aware that these two principles exist, and you need to be able to know which one you're actually working on. I am rich! I am rich! What's going on with Tolo? Let's check this out. Money, 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 da-da, must be funny, da-da, in the rich man's world. Money, money, money.